if you take an alloy out of any composition, this alloy is a single phase or a two phase, or single phase or double phase alloy? Yes, Panda, you are saying something. Somewhere you are saying yes. Somewhere your voice is not audible. Somewhere, can you repeat what you have told?
Sir, Mohammed wants to join.
Yes. Yeah, what you are saying? Can you repeat? Yeah, anybody want to speak? This is single phase or double phase?
Single phase alloy.
Okay, very good. Single phase. How single phase? How single phase? How you can justify single phase?
Because of homogeneous mixture.
Because of homogeneous mixture. Because of what is this? What is this? What is this?
Solid phase.
This is solid phase. What is the name of this solid phase?
Alpha.
Solid phase. Solid alpha solid phase. Okay, fine. But technically, what is this? Technically, what is this? Because this is A and this is B. So technically, this is a solid phase. But technical, what is name of this one?
Excuse me, sir. Mohammed wants to join.
I am not getting anything. Okay, view all. Yes. So what is this one? This is a solid phase and this is alpha. But what is the name of the alpha? Alpha is a what kind of substance?
Alloy.
Alpha is an alloy, that is fine, but alloy have many things. Alloy can be a compound, it can be a something else.
So it is a mixture of A and B.
It is a mixture. It is a mixture. Are you sure it is a mixture?
No,
Do you
sir.
remember the classification of an alloy? Alloy are classified into how many groups? Somebody have told the definition of a isomorphous system.
Solid solution.
Solid solution. Very good. A is soluble in B, B is soluble in A. So it is a solid. So it is a solid solution. If I will consider this one, this is also a single phase, but this is a liquid solution. I think you people got the answer.
Yes, sir. Yes, sir.
So this is a solid phase, but this is a solid solution. B is in solution with A is in solution with B, right? Complete solid solubility. So it is a solid solution. So strengthening mechanism will be what now? Tell me quickly. What is the strengthening mechanism?
Substitution and solid solution.
Yeah, name of the strengthening mechanism. If somebody will ask, what is the name of the strengthening mechanism?
Solid solution strengthening.
Yes, solid solution strengthening. Solid solution strengthening. Strengthening due to formation of a solid solution. But this is then substitution and solid solution. Very good. Done. Then now maximum strength composition. Can you figure it out? See, this sigma is nothing but the strength. This curve is showing you the strength. So maximum strength composition will be. Just look at the figure and tell me.
50%.
Yes, nearly 50%, 50-50. Very good. 50-50 weight% of A and B. Very good, very good. So you understand, everybody, what is the conclusion from this image? The conclusion from this image is, if we have a solid solution, we have a single phase alloy. If we have a solid solution, then strengthening mechanism is solid solution strengthening. And maximum strength where we'll get? We will get at a 50% A and B, right? You can see this is pure A, this is pure B. The strength is increasing. with increasing in the B percentage. And it reaches to the maximum. Similarly, suppose this is pure B, you are adding A. So strength of the B is also increasing with addition of A. And finally, it reaches to the maximum value. Okay, what is this point? And what is this point? Let me see who can answer. What is this point and what is this point?
Melting point of A and B.
Yes, very good. Melting point of the pure component. This is melting point of A and melting point of B. So can anybody figure it out? What is the relationship between this melting point and this one and melting point of this one? Let me see. You can figure it out. Carefully look at the figure.
Sir, higher the melting point, higher is the strength.
Yes, very good. Excellent. So higher is the melting point. Higher is the strength. Can you people tell me why this is happening? But this is actually room temperature strength. Don't forget about that. Higher is the melting point. Higher is the room temperature strength. Can you people answer this? Why, Panda? Can you answer that? Why, if melting point is high, why strength will be high? How can you correlate that? Why you on what basis melting point depends? How you can decide the melting point? It is higher or lower?
Bonding.
Bond strength, very good. Bond strength, how the bonding is there. If bond strength is very high, melting point will be high. Obviously, if the bond will be stronger, then strength will be higher in the room temperature. Right? Very good. Okay, now what is this figure? Just tell me quickly. Which kind of phase diagram is this?
Eutectic phase diagram.
Very good. Eutectic phase diagram. Eutectic phase diagram. How can anybody tell me how this is eutectic? How, from which part you can see is an eutectic phase diagram?
Sir, the liquid changes to alpha.
Yeah. Panda, your voice is not audible. Can you repeat?
Sir, liquid changes to alpha plus beta.
Liquid changes to alpha plus beta. Okay, fine. In that way, that means you are saying eutectic reaction is happening. That's why. Okay, forget about the eutectic reaction. Anything else? Let me see. Answer is lying in that thing only. Eutectic point. Something is happening in the eutectic point. What is the meaning of eutectic alloy? Let me see who remember that.
Easy melting alloy.
Easy melting alloy. Very good. The alloy which melts easily. Easily means at a low temperature, right? Now that is the answer. Can you tell me now?
So the alloy which has a lower melting point, then it's pure A and B, or
Okay, but from the phase diagram, just explain how this is a eutectic phase diagram. Panda has told very good one. The liquid is becoming two solid phases, alpha plus beta. The melting point is decreasing. Let's look at the melting point of pure A and pure B. And what is the melting point of this composition at this composition? You people now you people understand? You are adding B into A, the melting point is going down. You are adding A into B, the melting point is going down and meeting at a point. This is at this weight percentage of A and B, we have a minimum melting point of the alloy. Now you got the answer. And this is, what is this line called? Let me see, you can remember. What is this line?
Eutectic horizontal.
Eutectic horizontal. Very good. Eutectic horizontal. Very nice. Very good. Very good. Okay, fine. So now this is a single phase or double phase alloy?
Double phase.
Double phase. Very good. Double phase. Basically, if it depends upon the composition, you have to say, right? If I will take a composition here, then
Single phase alpha.
single phase. Very good. If I will take a composition here,
Single phase
single
beta.
phase. If I will take a composition here,
Two phase alpha and beta.
if I will take a composition here,
Two phase.
Same.
Very
Two.
good. If I will take a composition here,
Same. Two phase.
two phase. Very good. So basically, I am writing here double phase. You can write single phase depending upon the composition, double or single phase depending upon the composition. Basically, upon composition. Now, strengthening mechanism. This sigma represents the strength of the alloy. Strength. This sigma. So, strengthening mechanism will be what? You people told that strengthening mechanism here is the solid solution strengthening due to formation of a solid solution. So, here strengthening mechanism will be what? Let me see who can answer. First of all, tell me strengthening mechanism will be remain same or it will be variable?
So variable.
Variable, very good. Variable. How it is variable? Can anybody justify that?
So because A and B are different elements and their strength are different. So
What
with
you are
changing
saying? Here also
composition.
A and B are there.
Yes, so
Here
with
also in
changing
this. Huh.
yes, so with changing composition, the percentage of A and B changes, so strength will change of the alloy.
Okay, fine. This is also happening with the this system. Now you are changing in this weight percentage of B is changing. The strength is also changing. Here in this direction, your weight percentage of A is changing. The strength is changing.
Sir,
Before
in
answering
some
something,
part of
just
the diagram,
yes,
in
yes,
some part of the
yes,
diagram,
yes.
only
Some part
alpha
of the diagram.
is present. Only alpha and
Very
beta is
good.
present. Their
Yes.
strengthening mechanism is different. And where alpha plus beta both are present, strengthening mechanism will be different.
Very good. Very good. You people have studied IPM. I think you forget everything. How the strength or hardness depends. It depends upon the types of phases present. Yes or no? If you change a phase, the strength will remain same or different?
Different.
Different.
If suppose you have an
Different.
alpha phase, if you have an alpha phase, for example, then what I will do, I will add a beta phase into that. So strength will remain same in the material.
No, sir.
No, sir.
It will change because beta phase may be harder or softer. It depends upon that only. Now, similarly, suppose you have a beta phase, single phase beta in an alloy. Now, suppose I will add alpha phase into it. So strength will remain same or it will become different. It will remain same or it will become different the moment I will add alpha phase into the beta.
Different.
Different. So it depends upon what then? It depends upon the types of phase present. It is a soft phase or it is a hard phase. Yes or no?
Yes, sir.
Right? Very good. So now you can see. So final conclusion is what? What is okay? Can anybody remember what is this line called? Let me see. In an this eutectic phase diagram, what is this line? Anybody remember? But this line is not actually straight line. But for an explanation, I have drawn this straight line.
Solver's line.
Solver's line. Very
Solver's
remember
line.
that. This line is. Let me see how many of you remember.
Liquidus.
Liquidus line, and this is solver's line, and this line is what is this line?
Solidus line.
Solidus line.
Solidus.
Very good. You people remember that. I'm very happy with that. Yes, you remember. Solver's line is a line which separate two solid phases, right? Two different solid phases. What is this line?
Same. Solver's line.
Solver's line. Very good. So this is a single phase alpha, and this is a single phase beta. And these single phase are also called terminal solid solution. You have to remember that. This single phase is also called terminal solid solution because it is present in the extreme ends. Terminal. This is alpha is a terminal solid solution. Beta is also a terminal solid solution, right? So if this is a solid solution and this is a solid solution, then strengthening mechanism will be what? Up to this point and from here to here.
Solid solution strengthening.
Very good, very good. The strengthening mechanism will be solid solution strengthening. But what is the strengthening here from this point to this point? Just I have written over here. Just read it then from here to here. That means two-phase region. This is a two-phase region. Alpha is one phase, beta is another phase. What is the answer? Just tell me quickly. What is the strengthening over here in this alloy from this part to this part? Suppose alpha is your matrix and beta is a precipitate. So then this will be which kind of strengthening?
Precipitation strengthening.
Precipitation strengthening, right? Very good. So now the condition is what? If beta is a soft phase, then the strength will decrease. But can anybody tell me from this figure, the beta is a hard phase or soft phase? Just look at carefully figure. Look at the slope. You
Hard
can understand.
phase.
Very good. How you can justify hard phase?
Strength is increasing.
Strength is increasing. Very good. Very good. You can see the strength is increasing in this direction. That means beta is a precipitate and alpha is the matrix phase and beta precipitate is a stronger phase. That's why. So that means I can say from this point to this point, this is showing precipitation strengthening. And the property of or the strength of the material or the alloy depends upon the beta phase, and actually that depends upon the distribution of beta phase and volume fraction of beta phase. How much volume fraction of beta phase is present and how they are distributed and what is their size also. Now you people have understood? It depends upon the size and shape. It depends upon the nature of the phase. It is hard or soft, and also depend upon the volume fraction. How much amount of volume fraction of beta is present in this alloy, right? So volume fraction, size, shape, and distribution of beta phase decides the strength. Now everybody understood the answer, I think. If you have any doubt, you can ask me right here.
Sir, why composite strengthening?
You just tell me what is a composite if you remember from the IPM. Let me see. Very good question. What is a composite? Let me see who can answer.
Combination of matrix and reinforcement.
Okay, combination of matrix and reinforcement. But that is you are talking about what is inside the composite. But forget about that. But what is a composite material? If somebody will ask. Let me see you can remember. I have taught you this one in the earlier first or second class. I remember of IPM. Classification of engineering materials, if you remember. Ceramics, metals, and polymers. Then composites come. Then other classification is biomaterials and semiconductor materials. This is the classification of different materials. Metals, ceramics, polymers. Then comes composites. Then comes semiconductor and biomaterials. These are all classes of materials. Let me see who can remember. Suppose if I will add a polymer into a metal, this is a composite or not? If I will add a ceramics into a metal, this is a composite or not?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
it is a composite. Our rooftop is a composite or not? It is not a composite.
Composite.
How it is a composite?
Composite. Combination of phases, sir.
Combination of
Phases.
Combination of metals and cement, concrete.
cement concrete is a which kind of material? Polymer, ceramics, or metal?
Ceramic.
Ceramics.
Ceramics. Very good. So now that is the answer. Can you people tell me why this is having a composite strengthening? Because the beta is different phase, alpha is a different phase. You are now combining the two things. So it becomes a composite kind of material, yes or no? You understand now?
Yes, sir.
Yes, sir.
Because the property of beta is different to that of property of alpha. and composition of beta is different to that of composition of alpha. Composite materials means you are mixing two different kind of materials. Physically they are different, chemically they are different, and mechanically also they are different, you can say. That is a composite material. But just for a good explanation, I am saying this is having a composite strengthening, because nature of beta and alpha are different. Physically and chemically they are different actually. Now you understand now? Okay, but anyways, temperature solubility relation in terminal solid solution. So this is a terminal solid solution. This is a terminal solid solution. So can anyone tell me there is any relationship with the temperature? If temperature, you are increasing the temperature, the solubility is changing or not changing? In this figure, basically for in this figure, this is a cartoon diagram. Can anyone tell me if I am increasing the temperature, is there any change in solubility here?
Yes, sir.
No, sir.
No, obviously. Yes. Who is saying yes? Who is saying yes? Can you
Aditya.
justify?
Yes.
Yeah, Aditya, can you explain
No,
how
sir. No, sir.
from this image you are saying the solubility? Why no? Why no? Acha, in this direction, what should I write? If I will move the crusher like this, what should I write?
Composition.
Weight
This phase
percentage of B.
Weight percentage of V, very good. And in this direction, what I should write?
Temperature.
Temperature, very good. Now can you people tell me?
Yeah, varying temperature composition is not changing. The line
Very
is
good.
parallel to y-axis.
Line is a straight line. Very good. The line is straight line, right? So you can take this temperature, you can take this temperature, you can take this temperature, you can take this temperature. Solubility is fixed. There is no change in solubility. That means actually this is not a real diagram. You understand? Actually solubility changes. Anyway, so I am writing no change in solubility. Very good. But in the real situation, it changes because the diagram is not straight line. Can you remember how the diagram becomes? Instead of a straight line here, it moves. How? This solver's line is how actually in the real diagram?
So
This
like a
solver's
curve.
line.
So slightly a curve.
Like a curve.
Yes.
Curve, and how it will be? It will be like this, or it will be like this, or it will be like this, or it will be like this. This will be
The
like
last
this.
one.
Last one, very good. It will be like this. So if the curve will be like this, then solubility will depend upon temperature or not? No.
Yes.
Obviously, yes. That means solubility is increasing with increasing in the temperature, or solubility decreases with decreasing in the temperature. Same figure for this one also, it will be like this. Very good. Anyways, now we'll move to our precipitation strengthening. So precipitation strengthening, actually precipitate is what? Precipitate is a second phase particle. You can call precipitate as a particle. It is a second phase. So matrix is the primary phase and precipitate is a second phase, which basically come out from the matrix during the aging process. We'll see that. Aging means we are giving sufficient time to the alloy so that a particle will come out from the matrix due to decreasing in the solubility limit. Right? Anyways, so now precipitation strengthening means strengthening is occurring always due to interaction of dislocations with the particles here, right? So that means there is an interaction between dislocation and precipitate particles will be there. That leads to strengthening mechanism. So that means dislocation is moving in a material easily, but a moment will come when the dislocation will face a precipitate particle in front of it. So it will get stuck over there. It cannot move easily through the precipitate. So you have to apply more stress to move the dislocation again. So that leads to a strengthening mechanism. Right? So basically precipitates means aluminum copper alloy have a precipitate that is Al2Cu, if you remember. And brass also show precipitation strengthening. Super alloys also shows precipitation strengthening, like nickel based super alloys sometimes. And some certain steels also show precipitation strengthening. Precipitates, you understand, they are basically carbides or nitrides or carbonitrates. Precipitates are basically carbides, carbonitrates, or they may be nitrides, or some intermetallics. Can you people remember any intermetallic compound? It is very
L2Cu.
okay. Any other thing? Any in steels?
MNS.
MNS. Okay. Anyways, MNS is intermetallic. You can, but it is actually a
L2O3.
inclusion. L2O3. L2O3.
Yes, sir.
Intermetallic. Intermetallic. L2O3. Are you sure?
Because yes, sir, in secondary steel making, we basically deoxidate that to take out L2O3.
Yes, yes, yes. You are saying something. Yeah. In secondary steel making, what you are saying? Yeah. Can you repeat in secondary steel making?
Yes, sir. Secondary steel making, we basically deoxidize, remove oxygen from the
From the
steel.
steels. Yes, yes. So how you are removing oxygen from the steels?
Sir, I don't know, sir.
You don't know. How you can say you don't know? You have studied that in I think in degassing. Anybody remember degassing part in UP subject? Degassing of liquid metal, degassing of solids.
It's a by vacuum.
Yeah, vacuum is one method. Forget about that vacuum. But anything else that is related to the Ellingham diagram again? Steel contain dissolved oxygen, so you have to remove the oxygen. So what you need to add? You need to add certain elements which have more affinity to
So
the oxygen,
silicon,
which yes,
FeSi.
which can form more stable oxides. You got
Yes.
the answer. So aluminum is one of the best example, as you told. But if you add aluminum, what the product will be? Al2O3. Al2O3 is not a precipitate. It is a dispersoid. Oxides are basically dispersoid. Listen it carefully. You are getting my point?
Yes, sir.
Oxides are basically a dispersoid, like yttrium oxides, titanium oxides, aluminium oxide. These are dispersoid. But basically, precipitates are carbides, carbonitrates, and nitrites. It is okay now? Fe3C is an intermetallic compound. Cementite. Okay, anyways. So finally, I'll end the topic over here. So precipitation strengthening actually depend upon precipitate size and shape, volume fractions, nature of the interface between precipitate and matrix, and crystal structure of the precipitate. So these are the important points. Fine. So okay, we'll continue our lecture from the next class. Maybe today itself I will take the class in the next half.